Yeah, well, let's do an example, actually. And then this is the last example we'll do today. Next time we see each other, we will continue to have a lot of fun. And I know what you're going to say. Is it even possible to have more fun than today? Stop it, you all. Just stop. Okay. It's called Hooke's law. Okay. Okay, here we go. Here we go again. Same old stuff, dog, just a different day. Here we go again. All right. Yo, what up? Oh, that's not my wife. I got all excited. That's what, so that I could talk about study skills, right? Did I do that? Yeah, I talked about it for like 10 minutes, right? Yeah, I'm all good. What kind of nerd carries a digital scale in his back pocket? Kind of nerd pays thousands of dollars for his own labs? Because I love my students, right? That's called love. You feel it? I hope you feel it. I got a lot of it. Apparently that one doesn't work. That's all good. I got two. That's called coming for class. Oh yeah, that one works. Nice. That's called being prepared, right? Yeah. All right, so in Hooke's law, you know what we do? Okay. Yeah, so let's do this. Yeah, this is why your math teachers don't make math interesting. How long has this taken? You know how much this cost me? This is probably about 300 bucks right here. You know who paid for that? Well, actually, my wife allowed me to pay for it, right? You don't want to talk to the assistant manager. You want to go right to the CEO. I'll tell you that much right now. All right, so check this out. Hooke's law comes from this dude, let's call it a lady though, who sat in a room and had some way of measuring what we call masses, right? What this person did is just said like, oh, okay, so I'm gonna go ahead and take a look at that mass. Okay, so let's go ahead and start storing this data. So we're gonna have two places that we store data, right? And we better organize it in a way so that we know. Do you see this system here? So here we go. We're going to have what we call masses. And could you guess what else we're going to have? Positions. I'm not ready to talk about displacement yet. You guys are a little bit too, you're a little bit too advanced from old Anderson right now. You got to remember this man's feeble, right? You got to wait for this old man to catch up. Okay, so first one, we'll start with the smallest one. What is it? 10 something. 10 something. Could you guess what that is? 10.0 grams. Pretty good for like, okay. Then what do we do? Okay, well the first thing we should probably do is we should probably mark the initial position of the end of the spring. Why would I want to do that? So x0 is going to be the, I don't even want to call it x0. I want to call it, I don't even know what I want to call it. Initial position of end of spring. And maybe I'll call that x0. I don't know. All right? So I'm going to tell you this right now. This is a centimeter ruler. This right here is 1. You can come up after class if you want. You can touch it. Right? If you break it, you buy it. Right? So let's see. Let's do the little red mark. It looks like it's about 14 millimeters. I guess that would be probably centimeters, huh? Okay. And then I hang this thing, this little 10 mass on. You know what happens? Not a damn thing, because this thing's super stiff. Maybe you're not familiar with the difference between a stiff spring and a non-stiff spring, because how many of you played with springs before? I used to do this on Friday nights when my wife was working. 100% serious. I spent at least 3 Friday nights when she was working sitting in my room playing with springs so that I could design out this for you. And when I say Friday night, I mean literally from like 4 p.m. until like 1 a.m. Friday night. That's a non-stiff spring. You see it? Yeah. This is a stiff spring. The K on this spring is much higher than the K on this spring. No, I'm just kidding. Right? Okay, so what I do is I say to myself, like, okay, maybe the first position here, I'm going to call it like 14. And maybe it's like 14.01, but my eyes aren't calipers, right? So I'm going to say it's 14. So what do we do next? Grab the next one. And pray. Yeah, you all took it for granted that just masses like just show up in the world, right? Because that's what mathematicians do, right? Suppose you have a 10-gram mass. 10-gram mass. How do you know it's 10 grams? Show me the mass. This is a real-world problem. What's the problem? This is a real-world problem. Why is it a real-world problem? Because it can be studied by measuring data. Everything else, when you just write numbers down, that's called an ideal mathematicalization. If somebody told you Hooke's law and didn't make you do this, they lied to you. They told you the ideal version of that problem, not the real world problem. What's a real world problem? Measure with data. So what's the mass there? Damn, whoever got these masses, whoever made these needs to get a raise. It's pretty good, right? Okay, now what do we do? What do you think about my measuring data? No, it's pretty horrible, right? All right. Something about the West Coast. All right. We're almost done. You don't even want to leave, huh? You didn't even know it's 3:45 right now, huh? Yeah, that's called love. You're going to get the bug. I got the bug. You know what I dream? You know what I earn? Linear algebra. I swear to God. I pray for the moments that I can study linear algebra. I go through my whole day waiting for time to sit down and study this stuff. All right, I'm going to do this and then we'll leave, okay? If I did this forever, you know what would happen? I mean, forever, I mean, you say, let's say that I did every possible linear combination of all these masses, and I tracked them like this. What are you noticing about the individual coefficients? Coefficient 1, coefficient 2. Am I reorganizing these ones, or am I keeping them in the same order? Why would that be useful? So I pair this one with that, this one with that, this one with this. Am I writing them as a really, really long list this way? Why not? Because it's super hard to pair them. But if I write them in columns, and I put both columns right next to each other, what happens? Immediate bijection. Welcome to column vectors. That's it. That's a column vector. That's why we use column vectors, because it's much easier to read stuff down the page than it is to write it this way. Last thing I'm going to show you. Some of you have lives, right? I miss that. I have a very satisfying life, to be honest with you. But I miss like doing what I want when I want to do it. Oh, do I not have internet access right now? That sucks. It's all right, next time we see each other. Here, you want to see a data set? You want to see a vector?
Did you do this?
I did this. Yep. This is the first. You know how many times I've done this problem? Mike and I spent probably, how long we spent on our least squares problem for the eigenvalue analysis?
Long time.
Yeah. Him and I, this gentleman and me, we've published a paper on eigenvalues, and we probably spent, I don't know, 2 working weeks making sure that we understood everything about the spring we were using. That's the least squares problem. Claim. You know what's going to happen? You know the first person that was famous for knowing this, you know what this person's name was? Hooke. Hooke made data measurements, took masses, took positions, did some calculations with that, and noticed the larger the mass, the more it drops. And not only did he notice that, he noticed that the mass was directly proportional to the drop, aka the function that described this is linear. Oh, what are the chances we've studied linear functions in linear algebra?
Very high.
Welcome. I will see you again next time. This problem is going to be with us for the rest of class.